Hello, am I audible to you? Hello, good evening to all of you. Am I audible? Hello, guys, am I audible to you? Okay, good evening to all of you. Very good evening. Okay, very good. So, as I have given the assignments to you or homework to you, so have you gone through that homework? Yes or no? I had given some homework to you. Okay, please discuss that questions in the group only. Okay, then today uh, we will complete the non-ideal chapter. Today might be the last lecture for non-ideal. So as I told you कि I had started the last lecture with the numerical, but before that last lecture I told you कि just wait for a moment. Okay, so what I told you, good evening. What I told you in the last lecture, I started the RTD. Na? I told you that RTD is not sufficient to find the conversion in the real reactor except for the first order reaction. Although for the first order reaction I can use only RTD to find the conversion and production rate. Reason is that because the RTD is a first order process and the first order reaction is obviously a linear. So what I'm saying to you कि RTD is also linear, and why linear? RTD is linear means when you are using 10 gram of tracer material in the input, then the concentration, let's say this is the C core, and if you are using 20 gram of the tracer, then it increases by twice here. Here if the concentration is C1 at the time T1, then here it becomes 2C1. It means the concentration at that time is going to be increased by the twice. If you are going to increase the amount of tracer in the input, it means here the variation in the concentration is linear. Are you getting a point? That's why RTD is called a linear process. Since RTD is linear and the first order kinetics is also linear, that's why for the first order reaction RTD is sufficient to find the conversion. Okay, but for except for the first order reaction we can't use the only RTD to find the conversion, because in the we have seen in the last lecture कि if we are using the MFR, this system, let's say this is VM and here VP is there. And if you're going to replace the position VP here, and here VM is here, in that case the conversion is found to be different. Okay, now here early mixing is there, and here late mixing is there. Am I right? Because here the mixing is happening in CSTR and here mixing is happening in the CSTR, and it is a first here. So here early mixing and here late mixing is there. It means except for the RTD, RTD is only able to define what is happening at the exit. It does not provide any information about the what is happening inside the reactor, how the reactant molecules of different edges are going to interact with each other, and how they are going to process in the reactor. Okay, that's why RTD fails to define what is happening inside the reactor, or RTD fails about defining the mixing in the process, mixing in the reactor or mixing in the system. Okay, so in order to find the conversion or production rate in the real reactor except for the first reaction, we should also include the term called as earliness and lateness of the mixing. Am I right? And that's why to define the state of the mixing, we have already used the one parameter model and two parameter model. In one parameter model, I have already defined the Tankin series model. Tankin series model is used to define the performance of the real PFR, okay, for the plug flow reactor. And I told you when the number of tanks, it means when you have a PFR, and if the PFR is providing some different types of seeker, then you can find that this PFR is equivalent to how much number of equivalent CSTRs in series. Okay, so n is the parameter, and that n will define the state of the mixing, because when n equal to 1 then infinite mixing is there, and when n get increases, then what happen? The you have seen in the seeker variance is going to decrease, and when n equal to very large, then variance is found to be 0, because in the PFR no variance is there, and in the CSTR there is an infinite variance, or you can say variance equal to tau square. Am I right? So for all real PFR, the variance is going to lie between the 0 to tau square, because variance equal to tau square in the CSTR. Am I right? Yes or no? So Tankin series model is used to define the performance of a real PFR or tubular reactor. Similarly, I have one more model that we call as axial dispersion model that I have to cover today. So axial dispersion model is also the example of one parameter model, and here the dispersion number d upon ul I will discuss, that will define the state of the mixing. Now, so what I am saying to you, along with the RTD, we should also define the state of the mixing, and the state of the mixing is going to be defined by the one parameter model and multi-parameter model. Multi-parameter model is just like multi-parameter model is used to define the behavior of a CSTR. If you want to define the behavior of real CSTR, then you have to go for the multi-parameter model, because in the CSTR there will be problem of dead space, bypass and all. Okay, so we should go for the multi-parameter model. But as far as our syllabus is concerned, only I have a single parameter model and zero parameter model. So as far as zero parameter model is concerned, that I will discuss today. But as far as one parameter model is concerned or single parameter model is concerned, I already told you that model is only used to define the flow inside the vessel or reactor. I told you various example. Model flow in that real vessel is going to match with the Tankin series model. I told you, it means that model is used to define the types of mixing or flow inside the reactor or vessel that was absent in the RTD, because RTD only defined what is happening at the exit of the reactor. It was not able to define what is happening inside the reactor, and that's why to define what is happening inside the reactor, what is the flow, what types of flow condition is there inside, we should have another parameter, and for encounter that parameter, that types of flow conditions or that types of mixing, we should go for the models. And that's why I have told you one parameter model, multi-parameter model and zero parameter model. In one parameter model, I told you about the Tankin series model and axial dispersion model. I will discuss axial dispersion model today, but I already told you that Tankin series model. My dear student, Tankin series model and axial displacement model, both models are used to only define the behavior of a real plug flow reactor. If you have a real plug flow reactor, then you can model your real plug flow reactor or real vessel. A flow in the real plug flow may be matched with the Tankin series model or with the axial displacement model, and then we can find the conversion. I told you how can find the conversion in the real plug flow reactor by using Tankin series model. When the flow in the real plug flow reactor or real vessel is going to match with the Tankin series model, then I can use Tankin series model to find out the number of tanks in series, and then by knowing the number of tanks in series and number of CSTRs in series, I can find the conversion. I told you yes or no? But before going for the axial displacement model, I would like to complete the zero parameter model. Okay, so are you ready guys? समझ में आ गया link up? क्लियर है? Now, so here I am going to define here. The heading is use of RTD to predict the conversion. To predict the conversion. Use of RTD. It means only RTD I have to use to find the conversion. But you know, by use of RTD only I can find the conversion in the which order reaction? Please tell me. We know very well कि only RTD can be used to find the conversion. For which order of reaction? First order reaction. So here I will discuss ki how can you find the conversion for any other order of reaction by using only RTD. Okay, so first of all it is clear ki only RTD is not sufficient. Okay, very good. You know, only RTD, use of only RTD to find the conversion for the first order. For the rest order you should have some terms, some parameters that should be define what is happening inside the reactor, and that should be define the flow condition inside the reactor. Am I right? So in order to find the conversion in the real reactor by using RTD for any other order of reaction, I should define some terms, because if you want to find the conversion for in a real reactor by using only RTD, it is not possible. It is only possible for the first order reaction. Then if you want to find the conversion by using RTD for any order except than one, then you should define some terms that should be defined the mixing or flow condition in the reactor. Is this clear, sir? So here I will define the two terms. One is called as micro mixing and macro mixing. Micro mixing and macro mixing. Please listen, try to understand that. It is very, very important term. Micro mixing and macro mixing. These terms are often used in the context of non-ideal reactors. Micro mixing and macro mixing. What is macro mixing? Just listen. What is macro mixing? It is a overview of mixing taking place inside the reactor. And you know कि RTD will gives you an overview. RTD will gives you an overview of mixing taking place in the reactor. It does not provide the in-depth information about the mixing. Are you getting a point? So macro mixing is an overview or is a macroscopic view of the mixing taking place inside the reactor. It is not in-depth information about the mixing. Am I right? And you know कि RTD only able to define what is happening at the exit of the reactor. It means it will give you an overview or macroscopic view of the mixing in the reactor. So what I'm saying to you, RTD is a macroscopic analysis of the mixing inside the reactor. Am I right? Not the microscopic analysis. So macro mixing. Listen, macro mixing is a macroscopic view or overview of mixing taking place inside a reactor. And exit is or RTD, exit age distribution, also called RTD, residence time distribution, you know very well. Exit age distribution gives us overview of mixing. Am I right? Overview, Sujata. Overview of mixing taking place inside the reactor. Means what quality of mixing is there, that can be defined by three moments of the E curve. You know, three moments of the E curve. One is called as mean residence time, other is called as variance, and other called as skewness. So these three moments of the E curve by RTD, I told you कि I already found the three moments of the E curve. One is called as mean residence time, this is about the mean. One is called as variance, that is about the mean residence time about the origin. Second is called as variance, that is second moment of the E curve, this is about the mean. And third is called as skewness. The three moments of the E curve is actually defined only overview of the quality of the mixing, am I right? Not the microscopic analysis, it is only macroscopic analysis of the mixing. Clear hai, yes or no? The three moments of E curve give an overview of quality of mixing. And you know, my dear student, by RTD you are able to know na, by RTD you are able to know it is a PFR or CSTR. Now why it is overview? Listen, why it is overview? Because by knowing the RTD, because macro mixing is associated with RTD. Listen, macro mixing is associated with RTD because microscopic is, what is macro mixing? The macro mixing is an overview of the mixing taking place inside the reactor. It means you are able to know, by knowing the RTD you are able to know that this reactor is a CSTR or PFR. In ideal CSTR, you know the RTD is like that, है ना, exponential decay. It means if it is ideal CSTR, it means you can say infinite mixing is there. If it is a no residence time is there, it is a PFR. But all real reactor have some intermediate mixing is there. Am I right? Some intermediate mixing is there. So what I am saying to you, you are able to know one basic idea about the mixing, one overview of the mixing inside the reactor. Not detailed analysis, but overview you are getting by knowing the RTD, and that is called macro mixing. Is this clear, guys? For example, I've told you कि if the second moment of the E curve is 0, it means variance is 0. If the second moment of the E curve variance is 0, then no mixing is taking place in the reactor. You can say yes or no. No mixing is there. And if it is small, then you can say there is a less mixing is there. And if it is large, then you can say that vigorous mixing is there inside the reactor. It means only you are able to know overview of the mixing by knowing the RTD or by knowing the macro mixing, and that is called as macro mixing. Is this clear? Please tell me, is this clear? Clear है अनुष्का? Now, so you are able to know only the basic idea about the mixing by knowing the RTD, and that is called as macro mixing. Now please write micro mixing. Please write micro mixing. What is macro mixing? It is a microscopic view or detailed view, in bracket detailed view of the mixing taking place inside the reactor. Clear? It is detailed view of the mixing taking place inside the reactor. Exit is distribution or RTD does tell us time spent by different fluid element inside the reactor, but it cannot tell us the way the fluid of different ages, means different residence time group, different ages are interacting with each other inside the reactor. Okay, macro mixing is the information is the information on interaction between fluids of different ages inside the reactor. Clear है? Yes or no? So it is a detailed view of mixing taking place inside the reactor, because RTD only tells ki how much time is spent by the reacting fluid element in the reactor. It doesn't tell about the way the fluid of the different ages are going to interact. Is this clear? So it is not for 0 parameter, not for the 1 parameter. That's how I'm trying to simply normal 0 macro and micro. It is just used for non-ideal reactors. The term macro mixing and micro mixing, is this clear? Please tell me. Macro mixing is clear. So micro mixing is detailed analysis about the mixing, the way the fluid element of different ages are going to be interact. Now please tell me, what is the ultimate use of RTD? Why we did the RTD experiment? Just to find the conversion in the real reactor, yes or no? But what we found, कि only RTD is not sufficient. Why? Because we have seen कि either early mixing or late mixing, either early mixing first or late mixing first. In the both cases, we find the same conversion if we are using only RTD. It means along with the RTD, although the ultimate use of RTD to find the conversion for a given reactor, but along with the RTD we must have a model for what? Anyone? Model for micro mixing or macro mixing? Because macro mixing is RTD. So along with the macro mixing, you should have a model for micro mixing, yes or no? Because micro mixing will define what? Micro mixing will define the way of the fluid element or interacting of different age groups to each other. Sir, no one tell you in this way, sir. Just try to understand what I am saying to you. Means macro mixing is actually RTD. Macro mixing is what? Macro mixing is the overview of the mixing taking place in the reactor. I told you, and this is called as RTD. Macro mixing is RTD, yeah. And model for what? Micro mixing. Yeah, excellent. We should have a model for micro mixing. It means you should develop a model. You should develop a model, and that model should define the flow behavior. Means flow in the model should be matched with the actual flow in the reactor. Yes or no? जो आप model assume करोगे, whatever model you are assuming, that model have some parameters. That parameters should be vary. For example, in a one parameter model, n is the parameter which can be vary in order to match the result with the experimental results. Am I right? Yes or no? दोबारा समझो what I am saying to you. Everyone tell me, please. Is this clear? Yes or no? First of all, I told you, just forget about the macro and micro. What I am saying to you, I did RTD, and what we found, the drawback in RTD is that RTD is not sufficient to find the conversion, because although the ultimate use of RTD to find the conversion in the real reactor or production rate in the real reactor, but what we found, either you can use the CSTR first or PFR first, you will find the same conversion, but that is only correct for the first reaction. Except for the first reaction, that is not correct, and that's why we should have a worry for that. And that's why I used to define the two terms. One is called macro mixing and macro mixing. Macro mixing is just about the overview analysis, and that is called RTD. Because we know if the second moment of the curve, which is variance, if the variance is 0, because by RTD we can find the variance, है ना? And the variance is 0, then no mixing at all. If the variance is infinite, then infinite mixing is there. If variance is less, it means the less mixing is there. Means only I can say in that term by knowing the RTD. But how the molecules or different age groups are going to interact, that I can't say by the macro mixing or by RTD. For that we should know the macro mixing, and macro mixing is the detailed analysis about the mixing, and that's why we should have a model. We should develop a model, and that model have some parameter that can be vary. By varying the parameters in the model, some key parameters are there, and when we are going to vary the key parameters, then and why you should vary the key parameter? For example, in one parameter model, that key is what? N. If you are going to vary the n, what happen? If you are going to vary the n, then I can match the micro mixing results model. It means modeling result with the macroscopic results. Are you getting a point? Yes or no? Means there should be a proper match of the result that we obtain from the micro mixing model with the macroscopic model, with the macroscopic, or you can say by RTD, because ultimately the RTD is also define the overview of mixing, and it is define what is happening at the exit of the reactor. It means whatever the model we are going to assume for micro mixing, whatever model we are going to assume, that model should be defined what is actually happening, the way of interaction of the molecules of different age groups. So that model, any model, is only going to be correct when it is going to match with what? Any model. Model is just based on assumption. Model is just based on assumption, my dear student. So that model is only going to be correct when the results from the modeling is going to match with the when the results from the modeling is going to match with the when the results from the modeling is going to match with the results of RTD. Am I right? Then only na. So whatever results we are getting from modeling of the micro mixing, in order to know the detailed analysis, that results should be matched with the macroscopic or micro mixing model. Am I right? Macro mixing model. Clear hai? Yes or no? And that's why, just recall, in my dear student, what I'm saying to you, in a single parameter model. So single parameter model is a model of micro mixing. Means along with the what I'm saying to you, to find the performance equation. Listen, to find performance equation, what we must know, along with the RTD, along with the kinetics, one more thing we need. What? Anyone? To find the performance equation for the real reactor, along with the RTD, along with the kinetics of the reaction, we must know one more parameter, and that is called as model. That is called as model. That is called as model. Is this clear? How many of you got my point? So in order to find the performance equation, because only RTD and kinetics is sufficient, only RTD and kinetics, to if you want to find the conversion in a real reactor by using RTD only and by knowing the kinetics, we can only go for the first order reaction, not for any other order. But if you are going for any other order reaction, then along with RTD and kinetics, we must know the model. We must have a model. मेरे पास एक मॉडल होना चाहिए. वो मॉडल क्या बताएगा? That model will describe the extent of mixing. That model will describe the way of mixing, contacting pattern. Yeah, and that contacting pattern, I told you, in the ideal case only two contacting pattern is there. Yeah, Mr. Sankar. So what I am saying to you, RTD, now in non-ideal reactor, if you want to found, in ideal reactor only the kinetics and contacting pattern, because in the ideal cases only two contacting pattern is there. I told you, one is called as plug flow and mixed flow, infinite mixing and zero mixing. But in real reactor, the mixing is in between the two extent, and that's why we should have model to know what extent of mixing is there. To know extent of mixing, it is large, small, or what extent of mixing is there, we should have a model. Yes or no? And you should not have any model, you should not require any model only RTD and kinetics is sufficient. It is, now listen, for any order, but for first order performance equation is only function of RTD and kinetics. Is this clear? Bolo. Because coordinating pattern has been also already defined by RTD. Because if you, Mr. Sankar, as far as RTD is concerned, it is able to define ki what extent of mixing is there, means overview of mixing, and that is what, either perfect or zero mixing. So only RTD and kinetics is sufficient to find the conversion in the first order reaction. But as far as any other order of reaction, if you have a real reactor, then you must have RTD, kinetics, and you have model, and that model will describe extent of mixing or detailed analysis about the mixing. Is this clear? Now, and once you assume the model, listen, once you assume the model, then result of the modeling should be matched with the. So listen, what I am saying to you, the ultimate use of RTD is to find the conversion expected for a reactor with known kinetics. Is this clear? But this can be done by prescribing a model for micro mixing which is consistent with the experimentally observed macro mixing. Whatever we found for RTD, that model should be matched, means model results. If you suppose I have assumed Tanki series model, what I am saying to you, for example, I have used one model called as Tanki series model. In Tanki series model, what we found, ET curve like that, na? ET curve versus time. If you know ET equal to t ki power n upon tau ki power n minus 1 into e ki power minus t upon tau, whatever result we got here, factorial n minus 1. Let's say this is result we got here like that. So this result should be, this is, let's say this is ET versus time, and that should be matched with what? Suppose this we did by the model of Tanki series model. Now I have a real reactor here. Now this real reactor I did experiment. I have already one RTD here by the real reactor. This data should be matched with this data. This data should be matched with this data. Am I right? And once we find that this data is going to exactly match with this data, then I can find that that is the n. Let's say n equal to 4. For example, although I told you one thing here, although you can say in terms of variance, whatever variance is here, same variance is found to be n equal to 4. It means that real reactor flow in the real reactor is equivalent to n equal to 4 CSTR in series. Am I right? Means mixing in the, means the way of the fluid which are going to interact with each other is equivalent to the way the fluid is going to interact in 4 CSTR in series. Are you getting a point? Means that is the result from Tanki series model that should be matched with the RTD of the real reactor. And it means variance of this and variance of this is going to be equal, and from that I found the formula of sigma square equal to Tm square upon m. Am I right? Yes or no, Mr. Sankar? Are you able to visualize? If you want to go for graphical method, this is was the analytical method by equating the variance. Just you can open the notes. What I did here, I found the model, Tanki series model. For Tanki series model, I found the variance, general formula for variance for n reactors, and then I equate the variance for the real reactor, and then I found this formula. Then I can say this n will define the extent of mixing. It means the mixing, extent of mixing in that real vessel is equivalent to the mixing in the 4 CSTR in series. The way the fluid which is going to interact in 4 CSTR in series, the same way the fluid is going to interact in the real vessel. So this n is the adjustable parameter. This can be adjusted in order to match. This n can be adjusted to match the experimental results with the modeling result. And experimental result is called as macro mixing result, RTD result, and the modeling result is called as microscopic result. Am I right? Or results from the microscopic models. Or the one way is graphical method. Let's say you already did in this way. you have these types of curve for different value of n's. This is n equal to 1, this is n equal to, let's say this is 4, this is n equal to 20, this is n equal to, let's say 25, and this is the modeling result. Now this n can be vary, na? So let's say whatever the data you found from the experiment over the real vessel, this you can draw, and let's say this is going to be exactly match overlap on that. It means this n is 25. It means the flow in that real vessel is equivalent to 25 CSTRs in series. Am I right? So what I'm saying to you, only RDD is sufficient to find the conversion in only for first reaction. But if you want to find the conversion in for any other order reaction, along with the RTD, along with the microscopic result called as RTD result, you must also have a microscopic model, and that model have some adjustable parameter. That model must have an adjustable parameters, either one or multi. If one parameter is there, if only one adjustable parameter is there in the model, that model is called as, that model name is called as. If the model that we are going to use to know the extent of mixing, the way of mixing in the reactor, that model name is called as single parameter model. That model name is called as single parameter model. Clear? And the example is Tankin series model and axial dispersion model. Is this clear? That model name is called as Tankin series model or axial dispersion model. Single parameter. If only one adjustable parameter, it means by varying that parameter, I can match the result of modeling with the experimental results called RTD results. That's why this is the conclusion of all. I told you ki if you want to find the performance equation, then along with RTD and kinetics you must have a model, and if model have only one adjustable parameter, that name is called a single parameter model. And the name of single parameter model I told you is either Tankin series model or axial dispersion model. Now if you have more than one parameter, that name is called a multi-parameter model, multiple parameter model. If you have a two parameter, if you have two adjustable parameter, what example of two adjustable parameter, my dear student? Let's say in a CSTR, let's say if you have a real vessel, and you are going to approximate this as a bypass, and here some dead zone is there, here it is VB, and let's say this is V0, this is alpha times V0. Let's say for example it is VB here, and VB is the flow rate of bypass stream. This is the model, and this is, let's say, alpha into V0. Alpha into, it means alpha is the fraction. Then here VSB, what is VSB? 1 minus alpha into V0. Yes or no? If let's say 20% has been bypassed, but how I can know ki alpha is 20%? That I am going to say. Listen carefully. So this is the conclusion of all. Here what parameter I am discussing here? If we have a real vessel is there, let's say this is a real vessel, I don't know the flow behavior inside the reactor, but I know the RTD, I know the experimental ET core, I did the pulse experiment here, I find these types of ET core or RTD core we found for real vessel. This is your real reactor or real vessel or real reactor, let's say. It means this is the real reactor, and I have a kinetics. Let's say A equal to R. This is the first order reaction minus R. Let's say second order K into CS square. It is taking place. The kinetics is there. No? So you know the kinetics, you know the RTD, but only RTD and kinetics is not sufficient because it is second order reaction is there. Am I right? Along with the kinetics and RTD, you must have one more term that will define what is happening inside the reactor. And for that, let's say I have used this model. And this model is called as here CSTR with bypass and dead space. Let's say here this is V. Let's say this is called as beta into V, and this is 1 minus beta into V, where alpha is the fraction of the flow rate bypass. Alpha is the fraction of flow rate bypassed. Try to understand, sir. Although it is not in syllabus, but I just want, and beta is the fraction of the total volume, fraction of the volume which are active, fraction of volume which are mixed, and rest are 1 mass beta is unmixed. Is this clear? So alpha and beta, here two parameters are there, these two adjustable parameters are there. So I should have vary the value of alpha and beta such that if we are going to carry out the pulse experiment over that, yeah, very good, I should have this model. Let's say I can use any model, but let's say I have used this model. Nah, what I'm saying to you, I can use this model, but this model is correct or not, that can be decided by only the results that we are getting. Although if you are using Tanguy series model, that is only single parameter model. In that case, only one parameter was there to match, that was n. But here in this model, we have two parameters, alpha and beta. So what I'm saying to you, we should carry out the experiment over that. Okay, is this clear? So whatever CT curve we are getting here, whatever CT, if you are going to carry out the pulse RTD experiment over that, over this model, so whatever RTD you are getting over this model, let's say ET curve we are getting here, and this ET is a function of alpha and beta, yes or no? Because alpha and beta two parameters are there. So whatever ET curve you are getting, that is a function of two parameter alpha and beta. It means either this type of curve or this type of curve or this type of curve or this type of curve is there, that depends upon the value of alpha and beta, yes or no? That will depend upon the value of alpha and beta. So that curve is going to, for a given value of alpha and beta, because you can adjust the value of alpha and beta such that the result that we are getting from the model is going to match with the obtained from the RTD over the real vessel. Is this clear? Excellent, Shankar, you got the point. So I have two parameters here, alpha and beta. Then obviously it is difficult to adjust if parameter is going to increases, yes or no? Because in one parameter model, only one variable has to be adjusted, but here you have to adjust two parameter, alpha and beta. So you have to adjust the value of alpha and beta such that, let's say, I will show you one example. If alpha is found to be, let's say, 0.2, it means 20% is bypassed here, and beta is, let's say, here 80%. It means the results, it means whatever results we are getting from the model for the alpha equal to 0.2 and beta equal to 0.8, that is exactly going to match with the RTD results over the real vessel. It means the mixing in the vessel, mixing in that real vessel is equivalent to what? Is equivalent to, you have a CSTR in which 20% portion is going to be bypassed and 80% is of the volume is active and rest is inactive. Am I right? That's what I'm saying to you. And once you know this model, then we can find the conversion, because over applying the balance over that you can find the conversion. Hai ki nahi batao? Because the similar thing in the Tanguy series model, I told you, you have a one reactor, you have a n equal to 4. It means your behavior of a real reactor is equivalent to 4 ideal CSTR in series. Similarly here, if you have a real reactor and that real reactor behavior is equal to CSTR having 20% is bypassed and 80% is active, rest is inactive as a dead space, then we can find the material balance over that and find the conversion over that, because this reactor behavior is equivalent to this. Is this clear? And then we can find the conversion for any order except for the one. Clear? Clear? Is this clear to everyone? Yes or no? Mr. P. Ranjan, Sujata, Anushka. Obviously we should match na, because RTD will define ki what how much time is going to be spent. It is overview analysis. Then if microscopic is going to match, then overview should be also match. You know, in thermodynamics we have a two. Listen, what is the difference in the microscopic and macroscopic approach? If microscopic is going to be correct, then macroscopic is average of microscopic views. अगर microscopic analysis correct है, then obviously it should be obviously match with the average of that. And microscopic is RTD and it is a overview analysis, overall analysis and average analysis. तो एवरेज तो मैच करना ही चाहिए ना. Because macroscopic analysis is an overall effect of microscopic analysis, average of microscopic analysis. Are you getting a point? In thermodynamics, I will show you the two approaches there. One is called as classical approach, and another called as statistical approach. Classical approach, or you can say macroscopic approach and microscopic approach. So in thermodynamics, we are only bother about the macroscopic approach. Why? Because if the microscopic approach, it is a analysis at the micro level, at the molecule level. So I will not go for macro level because macroscopic analysis is an overview of, is an average of microscopic approach. Okay. So I think you got the single parameter and multiple parameter model. So what is role of model? It is clear. And did you got the information about the micro mixing and macro mixing? If anyone have doubt, you can ask me. So you can read many of the books, sir. Mr. Sankar, already you did the CRE. Have you cleared this point? Already you people have used the many books. You have read the many books. Mr. Neva. So I will take the time. I will always take the more lectures because what my purpose is just to clear all the concepts. Neva, clear है या नहीं? आने दो. Okay. Now now before starting zero parameter model, I already completed one parameter model, na? So please write one more question that will clear the concept. Please write one question. Please write one more question here. The question is the second order aqueous reaction A plus B gives R plus S is run in a large tank reactor. Large tank, he is not given the name. It is simply the second order aqueous phase reaction run in a large tank reactor, but it is not a CSTR. Having volume equal to 6 meter cube. Its volume of the vessel is 6 meter cube in which the reaction is taking place. And for an equimolar feed stream in bracket Ca naught equal to Cv naught. Conversion of the reactant is 60%. Conversion of a reactant is 60%. Unfortunately, agitation in our reactor is rather inadequate, insufficient, you can say inadequate, and tracer test of the flow within a reactor gives the flow model shown in the figure. It means model is given to you, means whatever it means, the model, listen, actually the agitation was insufficient, and the tracer test of the flow within the reactor gives the following flow model. It means that model is going to be matched with the tracer. Are you getting a point? Now the question is, what size of mixed flow will equal the performance of our present unit? How many of you got this question? Here, the first simple thing I am going to discuss here. V naught. This is the flow model. Its volume is 6 meter cube is itself. Okay. Now what it means here? How we got it is 1 by 3 from, because this is the result you are getting here, na? It means when the volumetric fluid, this is the alpha I told you. This alpha you got from matching the results of the tracer over this model with the result of the tracer over the real vessel, over the large tank. You have a little, this is large tank reactor is there. Large tank reactor is there having volume equal to 6 meter cube. You did the pulse experiment over that, na? You got some ET curve, RDD curve like that. Then that curve should be exactly matched with the model, and it is only going to match when alpha is found to be 1 by 3. This is already given to you. Are you getting a point? Yes or no? Now I think now it is going to be more clear to you people. How you got 1 by 3? By matching the RTD result over this model with the RTD result over the experiment, over the real vessel. Mr. Shankar, clear? Now the question is, the conversion is found to be 60%. Conversion is found to be 60%. It means the question is, in order to find the same 60% conversion, how much volume of the real ideal CSTR should be required? Means if the real, because this is real reactor, na? So real reactor use the 6 meter cube of volume to find the 60% conversion. If you want to attain the same conversion of 60% in ideal reactor, then what volume should be required? Now you got the question, yes or no? Did you got the question? And this is how much parameter is there? 1 parameter. So this is also 1 parameter model, because only the parameter is alpha, not beta is there. Beta is not there. It is example of 1 parameter model, and this 1 parameter model is used to define the behavior of real CSTR. No, it means what I can say, ki the flow in the real large vessel is equivalent to the flow of this reactor. matches, it is going to match. So this is a model, and for the model I got the parameter called as alpha, it is 1 by 3. Then how can I find? First of all, I should go the balance, I should go for the balance over this. My dear student, I should go for the A balance. Now let's say the A balance. If you go for A balance over this, because it is a CSTR is there, simple CSTR is there. So here it is 1 by 3, then 2 by 3 is going to enter here, 2 by 3 into V naught. So if you go for the balance over CSTR, then 2 by 3 into V naught into CA naught, because concentration will remain same, yes or no? Because simple stream is going to bypass here, so concentration here, here and here, it remains same, yes or no? So what is entering in the CSTR? If you see CSTR, the entering is here 2 by 3 into V naught. It is a volumetric flow rate. 1 by 3 is bypassed. The only 2 by 3 is going to enter here. I am going to apply the balance over CSTR only. So forget about all the other term. Only I should bother about this. Only I should bother about this section. The 2 by 3 into V naught into, it is FA naught. Now 2 by 3 into V naught into CA naught. It is a volumetric flow rate into concentration. Minus what is going to out here? I don't know what is going to out. But this will be again 2 by 3, because volumetric flow will be same here. It is a liquid phase reaction is there, and into CA here. It is going to be out here CA. Here I am talking about this point here. Minus of RA into V, and this is K into CA square. Why CA square? Because CA naught and CV naught are same and they are as per stoichiometric ratio. That's why this is the K into CA square. This should be equal to 0. Am I right? Into V, sorry. Into V. So from this what I can say here, 2 by 3 into V naught, this should be CA naught minus CA is equal to K into CA square, and V we are getting already, this is 6 meter cube. Listen, conversion is overall conversion. This 60% is not the conversion at this point, it is overall conversion here. The conversion at this point is different here. Try to understand what I am saying to you. Is this clear? So you can't say, you can't find the conversion directly here. I first find the concentration at this point. Let's say this point I am going to say as a C. This point, let's say this point is here. What I'm point? This point is 1, this point is 2, and this point is 3. So it is KCA2 square. Is this clear? And this is also CA2. Equation number 1. Now you can make the balance over this point here. Let's say this is mixing point called M. Over the mixing point, what is going to happen? The streams are going to mix here. Here it is CA1. Here already the concentration is CA0. Here let's say it is CA3. Am I right? At the mixing point M. If you see, and here if you go for material balance for A, then here it is volumetric fluid is 1 by 3 into V naught. Here 2 by 3 into V naught, and here summation of this plus this, 2 by 3 plus 1 by 3, it is simply V naught. Am I right? Then if you go for the A balance over this point, what you are getting here, 1 by 3 into V naught into CA naught plus 2 by 3 into V naught into CA1. This is equal to V naught into CA3. My dear student, V naught cancel, and you know CA3, because conversion is given to you 60% overall conversion. It means CA3, because it is real reactor, no performance, means CA3 equal to Ca naught into 1 minus Xa. Are you getting yes or no? Ca naught based on initial concentration. So we can find the Ca3, and this is Ca naught into 1 minus 0.6, my dear student. Then it is 0.4 into Ca naught, Ca3. So please 1 by 3 into Ca naught plus 2 by 3 into Ca1, and this is equal to 0.4 into Ca naught. This is Ca3. Please find the C1 in terms of Ca naught. Yes or no, Mehna? Yeah, it is Ca2. No problem, ma'am. It is Ca2. Sorry, Ca2. Now clear, ma'am? So from this equation, can you find the Ca2 in terms of Ca naught? Yes or no? And once you know the Ca2, put here and find the value of unknown quantities. Unknown quantities what? K, V naught and Ca naught. Are you getting a point? It's too simple. A simple a part of material balance. So here 2 by 3 into Ca2 is equal to 1 by 3 into Ca naught minus 0.4 into Ca naught, then Ca naught equal to 1 by 3 minus 0.4. Oh, something is going wrong. Please do check here again. कुछ गलत हो गया. Ma'am, here this volume is 6 meter cube now, because this is the, ma'am, actually I have to find the volume of ideal CSTR when there is no bypass and all. Here is square. Ma'am, I have to find the volume of CSTR when I have no any other bypass, and but this is for real. This assembly is real assembly, ना? Real assembly is equal to this. What I'm कुछ मिस्टेक हुआ, चेक करिए आप लोग. Oh, sorry. Here, Mehna, are you getting a point? Yes or no? Very good. So please find the Ca2 is 0.1. Mehna, are you getting a point? Yes or no? Mehna, समझ में आ रहा है? What I had to calculate the volume. This is the volume of real vessel, na, 6 meter cube. Because real vessel is going to be, I have to find out this volume when only V naught is there and out here, no bypass, no other is there. Yeah, Ca2 equal to 0.1 into Ca naught. Please put in this equation. Please put in this equation Ca2 equal to 0.1 Ca naught here, and find the value of, this is 2 by 3 into V naught into Ca naught minus 0.1 into Ca naught is equal to K into 0.1 का square into Ca naught square into 6. Then 1 Ca naught cancel. Then please tell me K Ca naught upon V naught. This value you can get here, and this K kinetics and volumetric fluid will not change. Is this clear? And once you find the K C naught into V naught, please tell me what is the value of this. Ma'am, this is the real vessel. Behavior of real liter is equivalent to this. Are you getting a point? So please tell me what is the K C naught upon V naught. Now they are asking for what size of MFR is required for equal performance for the present unit. Whatever unit have, that must same performance as in the single CSTR. So what I did here, I have to use the single CSTR having volume is unknown, volumetric flow rate is same as the previous, and this is the reaction. And I have to convert the X equal to 0.6 again to same performance. So you know, in this V upon Fa naught is equal to Xa upon K into Ca naught square 1 minus Xa ka whole square, because the second order reaction is there. Fa naught equal to Ca naught into V naught, Xa upon K into Ca naught square 1 minus Xa ka whole square, 1 Ca naught cancel. Then from this equation you can find the K into Ca naught upon V naught is equal to V Xa upon 1 minus Xa ka whole square, Xa minus 0.6 here, 1 minus 0.6 ka whole square, and this value you already got. Find the volume. Whatever value you got here you can put from the last. Okay, if it is 10, then find the volume. It is 0.6 upon 0.4 ka whole square upon 10. This is the volume in meter cube you are getting, and obviously it will take the lesser volume. Please tell me. When it is ideal, then obviously for the given conversion it will require less volume. Did you got my point? Now this is again one parameter model. This 6 meter cube was for the real vessel volume was 6 meter cube, but now if you are using ideal CSTR to find the same conversion, it is taking only how much volume? Okay, 0. It is too much small when it is ideal. Mehna, clear? Mr. Priranjan. Now please repeat the same question for the second model. For the same question, the first model was this. Now the second model I am going to write here. It is for your homework. Everyone has to do, otherwise you people will suffer the problem. Then you should not say to me it is 0.8 into V naught. It is V naught. Then obviously the remaining is 0.2 V naught. It is common sense. Here again the conversion is 60%. Here V naught. Here its volume is 2 meter cube and rest 4 meter cube is a dead space. This is, it is bypass with dead space. So obviously this out of 6, 2 meter cube is there, means how much percent? 1 by 3. Huh? So 1/3 volume is here active and rest 2 by 3 is dead. And here 80% is going to 20% is going to bypass. So that alpha and beta you are getting from the experiment. Huh? So for the same, how much question is this equivalent to how much a single CSTR having volume how what when the V naught and here it is V naught, how much volume should be required? Can you do as a homework? So although I had this is the just I told you it is this is 2 parameter model. Why? Because here alpha and beta both are there. If you compare with this model, I told you already This is, if you recall, my dear student, this is alpha into V naught, this is beta into V, and this is 1 minus beta into V, and here 1 minus alpha into V. Here two parameter alpha and beta is there. This alpha and beta we got from the experiment by matching the tracer experiment, by matching the RDD over the model and over the real vessel. Then we got the alpha and beta. Here two parameter was there, means alpha and beta has been varied such that here alpha is found to be 0.2 and beta is found to be, if you see, beta is found to be 1/3, so that the flow behavior in that model is going to match with the experimental results. Are you getting it? Here two parameters, the alpha and beta. This is the example of multiple parameter model. Clear? So similar exercise you should do here as I did in the past. Nothing special. Clear? So still I did not started the zero parameter model. I only discuss about the two types of mixing that is frequently used in the non-ideal reactor, that is called as micro and micro mixing, and then I describe the one parameter model and multiple parameter model. Okay, and I told you कि along with the RDD and given kinetics, मैम बी 1/3 कैसे, बीटा 1/3 कैसे हुआ भाई? पूरा वॉल्यूम 6 मीटर क्यूब है, तो 6 का 1/3 कितना हो गया? पूरा वॉल्यूम तो 6 मीटर क्यूब था ना मैम। अरे यार, तो 6 का 1/3 कितना हुआ? 2 हुआ ना। ये 2 मीटर क्यूब लिखा तो है क्वेश्चन में, ये 2 मीटर क्यूब लिखा हुआ नहीं लिखा हुआ है, ये 4 मीटर क्यूब लिखा नहीं हुआ है। तो इसका मतलब क्या है भाई? मैं ये बीटा इंटू बीटा फ्रैक्शन है वॉल्यूम का, पूरे वॉल्यूम का। पूरा वॉल्यूम 6 मीटर क्यूब है, तो 6 मीटर क्यूब का केवल 2 ही मीटर क्यूब तो एक्टिव है, रेस्ट क्या है? इनएक्टिव है। तो ये 1/3, ये 1/3 आया कैसे? दैट इज ऑब्टेन फ्रॉम द एक्सपेरिमेंट। मैम अल्फा और बीटा को वेरी करोगे, इफ़ यू वेरी द अल्फा एंड बीटा देन योर, मैम मिस्टर मिहिर द सेम क्वेश्चन इज देयर, मिस्टर मिहिर सेम क्वेश्चन फॉर द सेम क्वेश्चन आई टोल्ड यू ना, सेम क्वेश्चन इज देयर। How you found, Sujata, how you find the value of alpha and beta? I told you now, if you, let's say you have a known alpha and beta, you started carrying the experiment over that, apply the tracer balance, then you find the ET curve as a function of alpha and beta. Now vary the alpha and beta such that whatever ET curve you obtain from this model is going to match with the ET curve over the real vessel. Then that alpha and beta are the value of parameters which matches the result of the modeling with the experimental. Clear hai? So what I am telling you here, I still not started the zero parameter model. I only told you कि RDD is only RDD along with the kinetics of the reaction is used to find the conversion only for the first reaction. Except for the first order reaction, the performance equation is based on the kinetics, RDD and model. You must have model. So for zero parameter model, although the adjustable parameter is 0, I should not vary any parameter. Just for example, in one parameter model, although model is always there, model should be always there, because without model we are not supposed to find the conversion for any order except than 1, because all other order are non-linear processes. Only first order is linear, RDD is linear and first order is linear, first order kinetics is linear. That's why I should not go for any model in the first reaction. But except for the first reaction, you always must have a model. So in zero parameter model, I should not vary any parameters. Just like in a first parameter model, we have varied the n. In Tanki series model, we will vary the dispersion number d by ul in axial dispersion model. I had varied here the value of alpha. Here I had in multiple parameter model, here I had value alpha and beta. But in zero parameter model, there is no any adjustable parameter. There is no any adjustable parameter, but there must be a model, and that model is based on two types state of the fluid. I will assume the two types of fluid. One is called as macro fluid and micro fluid. Here I am just leaving you for a break with some important terminology that is going to use in the next episode. That is what macro fluid and micro fluid. Although in zero parameter model I told you there is no any parameter which you can vary. That's why the name is called zero parameter model. But model is always there. So what model? That model should be defined the way of mixing. Detailed analysis about the mixing, and that detailed analysis about the mixing can be known by the knowing the state of the fluid. So we will assume the two state of the fluid. One is called as macro fluid and micro fluid. Are you getting it? Macro and micro fluid, not mixing. So mixing is different thing. Macro and micro mixing is different thing. I already cleared. You should not merge the points here. So macro and for which second one or first one? So what I am saying to you, Mr. Neva, try to listen. No, I am not giving you a number to solve the question as early as possible. Na? If you solve early, then I will not give you a number. But if you listen, then definitely you will get knowledge. What I am saying to you, try to understand. In zero parameter model, I will not give you any parameter to adjust. I will assume a model that is based on the two types of fluid, that is called as macro fluid and micro fluid. Macro and micro fluid, not mixing. Macro fluid and micro fluid, and that macro fluid is also called as complete segregation model, and the micro fluid is the maximum mixedness model. Are you getting? So in zero parameter model, two parameters there. One is called as complete segregation, and other is called as maximum mixedness. Have you heard about the name? So today I will complete this lecture. Please go for your dinner. Come at 9 fast. What happened, Sujata? Why you are crying? Hello. Am I audible to you? Sujata, am I audible? Okay. Abhinando. Okay, now please write down heading is here, zero parameter model. In zero parameter model, RTD is such used to estimate the conversion. Means in this case we should use the RTD as such, but still to get the conversion we need to prescribe a model for micro mixing, as I told you, na? Here also we have to prescribe a model for micro mixing, na? To estimate the conversion. Clear? And there are two extreme of micro mixing is there. Two extreme of micro mixing are possible. Means detailed analysis. You know, micro mixing means detailed analysis. The two extreme of micro mixing are possible. One extreme of micro mixing is that the two extreme of micro mixing is possible. What are those two extreme? One extreme of micro mixing is that the fluid elements of different ages do not mix with each others inside the reactor. They do not mix inside the reactor. Okay, means the two extent of mixing is there. The two extent of micro mixing is there. One extent of micro mixing is the two extent of micro mixing is there. One extent of micro mixing is that in that micro mixing the fluid of different ages do not mix, they not coalesce, they do not coalesce to each other inside the reactor. Okay, and the other extreme of micro mixing is that the fluid elements of different ages are mixing with each other as early as possible. Okay, means one have the two extreme of micro mixing is there. One mixing have you can say latest mixing is there, other have earliest mixing is there. Earliest mixing means as soon as possible they are going to mix with the different age groups. Another extent of mixing is there where the mixing is latest, means they do not mix throughout the reactor with the different age group of molecules. Okay, and these two extremes views on micro mixing gives rise to the concept of two fluids, microfluid and microfluid. Clear? Means there are two extent of micro mixing is there. Listen, this is two extent of micro mixing. One have segregation, complete segregation. This is a model of micro mixing, complete segregation. And other extent is here their scale of micro mixing, and other have maximum mixedness, means complete mixing, complete segregation and maximum segregation, or sorry, complete segregation and maximum mixedness. Clear? And that is what, this is the scale, and this is called degree of segregation. This scale is also called as degree of DEGREE of segregation. And this is here intermediate, complete segregation mixing, maximum mixedness, and there is a intermediate mixing is there in between. Intermediate mixing is there. Clear है? Yes or no? So what happened in that model? I have a micro mixing scale. This is scale of micro mixing, and also called as degree of segregation in the Levenspiel. So this micro mixing, this is the scale of micro mixing. The scale of micro mixing has been also used replace the word called as degree of segregation by the Levenspiel. In the Levenspiel book, they have used the word degree of segregation. The degree of segregation is the two. One extent is complete segregation, other is maximum mixedness. Okay, and that will rise the concept of two fluid. One is called as macrofluid and microfluid. Means actually the micro mixing is a degree of segregation, and the macro mixing is what? It is all about RTD. So segregated flow means here late mixing is there, am I right? Means mixing is late mixing, and here earliest mixing, latest mixing is there. In this case, latest mixing. Latest means as late as possible, latest mixing, and here earliest mixing. Clear? How many of you got this point? Because I told you in zero parameter model also we have to assume the model, and the model is the model for what? Micro mixing. So as far as model is concerned, the two extreme of micro mixing are possible. One is complete segregation, one extreme, other extreme is maximum mixedness. In complete segregation model, the mixing is latest. Mixing is latest means as late as possible, means there no mixing at all. Mixing is only at the exit of the reactor, not inside the reactor. And here it is corresponds to the earliest mixing. Mixing is as early as possible, called as maximum mixedness. And that concept will rise to the two types of fluid, rise to the so these extremes views on micro mixing. These two, I told you, the two extremes of the micro mixing give rise to the concept of two fluids. One is called as macrofluid and microfluid. Okay. And this all concept I am going to rise just to clear the concept of early and late as a mixing, because I have seen when n is more than 1, then obviously which is favor, early mixing or late mixing? When n is more than 1, then obviously we have seen the CSTR and PFR, and out of PFR and CSTR the better arrangement is this one. It means here mixing is late, and here it is early. This n more than 1, this is favor, and n less than 1, then early mixing is favor. Am I right? So in order to define the early and late of the mixing that was absent in the RTD, I am going to define these terms, which is called as complete segregation model and maximum mixedness model. and that complete segregation model indicates you the latest mixing, and the maximum mixing model will show the earliest mixing, latest and earliest. Now the question is, what I'm saying to you, early and late, how much early and how much late? It is vague term. Vague term, do you know vague term? Vague term means confusing term, and in engineering we should have a clear term. So why it is vague term? Because early, how much early? Even 2 minutes late is not late for me, although it is late for you. So how much late, how much early? If I am early for 1 minute, then how much early? Even the 1 minute is not too much early. So it is confusing term na, ki early and late, but how much early and how much late? In order to define how much early and how much late, it is vague term, a confusing term. In order to clarify this term, I have used the term called as complete segregation model to extent of micro mixing. Means these are models, and that's the name is called as complete segregation model and maximum mixage model. So in zero parameter model, the two model is there. One is called as complete segregation model, and second is called as maximum mixedness model. In that model, the mixing is, in complete segregation model, the mixing is latest, and that extent of the two extent of mixing will give rise the concept of two fluids called macro and macro. Is this clear? So write down please. These extremes of micro mixing give rise to the concept of macro fluid and micro fluid. Macro fluid or micro fluid, clear? बोलो. What is macro fluid? First is macro fluid. The macro fluid is what? A fluid in which the fluid elements of different ages do not mix. That I told you, the two extreme. One is complete segregation. So macro fluid has a capability to do not mix. And why is the macro fluid have a capability to do mix? They are capable of mixing. The macro fluid are the fluid elements which are not have a ability to mix or collize. So what happened here? In the macro fluid, my dear student, it is a fluid in which fluid elements of different ages do not mix with each other. It means molecules of a fluid element of a given age are restricted to remain inside molecules of a fluid element of a given age are not allowed to mix. Okay, it means in this case molecules of the fluid element of given ages are not allowed to mix. Of given ages of fluid elements of given age, means same age, are combined to each other and do not interact with fluid element of different age group throughout the reactor. Clear? It means in this case what happened, for example, listen, if it is a macro fluid is there and it is going to happen here entering in the reactor, so there what happened, the fluid elements of the same age group, means for example let's say you people are from the chemical engineering group, so you people of chemical engineering groups are going to combine to each other, and the other peoples of the same civil branch are going to combine to each other. Similarly here, the fluid elements which have same age, means which are going to spend the same time, let's say it is spending 2 seconds here from inlet to exit, it is exit is here. The fluid elements which have the residence time of 2 seconds, they are going to combine to each other and they will form the cluster, a group of molecules, and they are remain in form of packets. They are packets of the different molecules, and all molecules in a packet have the same age. And here one packet is there, and in each packets there is a large number of molecules are there, and they have residence time, let's say 5 seconds or 4 seconds. Here one more packet is there, and here it has a residence time of let's say 3 seconds. Means in this macro fluid, the fluid element of same age groups are combined to each other and they form a cluster. But they are not allowed to interact with the packets of the other molecules of the different age groups. Are you getting it? Means throughout the molecule, this is the packet of all the molecules, and in each packet there is a molecules of 10 to the power 12 to 10 to the power 18 molecules are there in each packet. It means molecules, in this case in the macro fluid, the molecules of the same age group combine to each other, and you can write here combine to each other and form a cluster, dher, CLUSTURE, form a cluster. Fluid element of a given age, or you can say same age, are combined to each other and form a cluster, also called as packets. In each packets there are nearly 10 to the power 12 to 10 to the power 18 molecules are there, but each molecules are same age group, that's why they are a packet of one age group, but they do not going to interact with the fluid elements of different age groups. Is this clear? Throughout the reactor, and that's why there is a complete segregation is there. That name is called complete segregation. Do you know complete segregation means? There is no any interaction of the one packet with the other packet, and every packet have more number of molecules. Okay. And if every packet have different, let's say here T1 is there, here T2 is there, here T3, they are age group. In that packets, all the molecules have the age group T3, all the molecules have age group T2, here T1, T3, like that. Then obviously, and each packets will act as a batch reactor, and each packet, because it's common sense to say कि if in a single packets every molecules are going to spend the time of T1 here, it means the conversion we can define as a every packets will be act as a batch reactor, because they are going to spend only time T1 here. Then conversion in that is x1, here conversion is x2, here conversion is x3. In each packet the conversion is different, because each packet will spend different time in the reactor. Clear? How many of you got this point? So in that macrofluid or complete segregation model also, because I told you the macro mixing model which assumes the fluid as a macrofluid, the complete segregation, I told you now, micro mixing model, the microscope, because they are the model at two extent of the model is there. One is called as complete segregation and maximum is there. The macrofluid is the fluid, or you can say the model of micro mixing. The micro mixing model which assumes the fluid to be a macrofluid is called as segregation model. That indicates the fluid of different age groups or fluid of same age groups are combined to each other, form a cluster, and they do not interact with the packets of the other age group molecules throughout the reactor, and every packets will act as a batch reactor, small batch reactors. Clear hai? Yes or no, Sujata? So because they are the model, na? Model of what? Just you can think here, they are the model of their extent of micro mixing with complete segregation and maximum mixedness. So in the model of the micro mixing which assumes the fluid to be a macrofluid, that model is called as complete segregation model. Why complete segregation? There is a no interaction of the molecules of the same age group with the other age group. So molecules of same age group will form a cluster. For example, if you are in a college and if your courses is for 2 year, another person have courses of 3 year, then person of the, because they will leave the college, one group will leave the college after 2 year, other groups will leave the college for 3 year, other groups will leave the college after 4 year. Means duration for leaving the college is different. It means the residence time for the different groups are different. Yes or no? It means the person who are going to spend the 2 years, they are form a groups, and they are not going to interact with the person who are going to enroll for the course of 3 year, and that they peoples are not going to interact with the person who are going to enroll for the 3 year course or 4 year course. So what happened? Let's say the college, and this college is just a reactor, and the packets are the 3 packets. One have 2 year, 3 year, and 4 year. The persons are going to enroll for the 3 courses. One is 2 year course, other is 3 year course, and 4 year course. The person having 2 year course are going to collect to each other and form. They just made a group, and they will spend only 2 year in the college. And here the person who are going to spend enroll for 3 year course, they are going to combine to each other, and they are going to form a group, and that will spend only 3 years, and they are 4 years similarly. Okay, so what happens, since they are going to, every packets are going to spend different time, that's why every packets will act as a small batch reactors, and in each packets the conversion is going to be different. Yes or no? Why conversion is different? Because since each packets is going to act as a batch reactor, that's why, and since the time is going to spend in the reactor is different, that's why the conversion is different. Yes or no? And that model is called as this is the model of micro mixing. Means the model of micro mixing which assumes the fluid to be a macrofluid. It means complete segregation. That model name is called complete segregation model. Clear? Follow. And here I can expect the latest mixing is there. Mixing is not in the reactor, because I told you there is no interaction. Means the molecules of different age groups are not going to interact. They are only going to interact at the exit only. Means how can find the mean conversion? Because I told you कि different elements of the different packets different packets will spend different time in the reactor, and that's why how can find the mean conversion? Because conversion is different for all packets. So in order to find the conversion, what we should do, कि although at the exit no mixing inside, only the mixing is taking place at the exit, like the latest mixing is there. So it means the microfluid has a ability of latest mixing. Microfluid has a ability of latest mixing, am I right? Means in order to find the conversion, if you want to find the conversion for the macrofluid, what we should do? If you want to find the conversion for the macrofluid, how can you find the conversion? Can you tell me? If you want to find the conversion for the macrofluid, then we are going to assume ki here, although there is no any interaction between the two different age groups, but when they are going to come at the exit, the packets whose life expectancy is the same or different, they are going to mix to each other, and they are going to provide the average conversion. We should have go for average. Why average? Because I told you the residence time is different. What happened? It means life expectancy are different for different age groups molecules. So if you want to find the conversion for that, listen please, you can write this. What do you have written here? Macrofluid. And here you can write each packet will act as a small ideal batch reactor. A small ideal batch reactor. And the micro mixing model which assumes the fluid to be a macrofluid is called as complete segregation model. Complete segregation model. Okay. And if you want to find the conversion for that, then mean conversion I can calculate by sum of conversion at time t. It means at time t, let's say this is the macrofluid is there, and I told you at time t the fluid whose life expectancy, or you can say the fluid who have spent the different time in the reactor will come out here. Let's say I am going to say कि this at time t one packet has been come out who has spent the time t, na? And you can sum up the all, and this should be multiplied because all the fraction will not come out. Because what I'm saying to you, it may be possible, it depends upon the life expectancy. Because in this case, it may be possible कि molecules of lower age group, lower age has not come, they are inside, and the molecules having higher age group, sorry, it is not possible. What I'm saying to you, this is xt into E of t. E of t is what? It is a fraction. You know, et dt is what? What is et dt? It is a fraction of the tracer material which are coming out. A fraction of the material which are coming out in time t and t plus dt. And if you're going to multiply with xt at that time t, what conversion we are getting here? Xt is the conversion of different age group who are going to be mixed to each other. Because although there is no mixing of different age group, but when they're going to come out, they're going to mix. All molecules of the different, all the packets of different age are going to mix, and they're going to just add. This is, and otherwise if continuous function is there, you can write like x of t into E of t into dt, and this is x of t of what? It is a batch. It is a batch because every packets will act as a batch reactor. So at that time t, what is the conversion of that packet into e of t dt, because et dt is the fraction that is coming out that time t. Okay, and this will depend upon, if it is a pfr, then every molecules will come at the same time. Is this clear? xt you can find from the batch 0 to infinity. So x bar equal to sorry, x of t e of t into dt. This is how we can find the mean conversion of macrofluid by complete segregation model. Clear hai? And how can you find this xt? This xt can be calculated from batch reactor formula. Because depending upon although their residence time are same, what I'm saying to you, try to understand what is life expectancy and what is residence time. Although the fluid elements residence times are going to be different, but their life expectancy may be same. Means it is possible ki the packets of two different age groups may have the same life expectancy. Okay, for example, what is meaning of life expectancy? Suppose I born in 1989, you born in 2020, sorry, let's say 2013, but both people got an accident and they got died at the same time. It means their residence time are different, but the life expectancy is same. Yes or no? Are you getting it? The two persons are there, they have born at different years, their residence time is different in this world, but their life expectancy is same. Means both is going to be died at the same time. Is this clear? Ma'am, it is all about average, because I told you now in that if you have macro, not reactor, if you have a macrofluid, then in macrofluid the fluid elements of in each packets I've told you there is 10 power 12 to 10 power 19 molecules are there, 18 molecules are there, and these packets have different conversion. Here x1, here x2, here x3, here x4. Okay, now then how can find the average of that? Average of that you can simply found by taking the average at that time, because at exit what is coming in time t and t plus dt, in time t and t plus dt how much fraction of the material is coming. मैं ना कुछ नहीं करना है, बस समझो यहाँ पे मैम, यहाँ समझिए, भूल जाइए सब कुछ। मैं क्या बोल रहा हूँ मैम, यहाँ पे दो एक अलग एज ग्रुप का है, यहाँ 2 सेकंड है, यहाँ 3 सेकंड है, 4 सेकंड, 5 सेकंड। इन एवरी हेयर कन्वर्जन इज डिफरेंट इन ईच बैच, बिकॉज एवरी पैकेट विल एक्ट एज अ बैच रिएक्टर मैम, है ना। एवरी पैकेट विल एक्ट एज अ बैच रिएक्टर, एंड सिंस एवरी बैच is not going to interact with other packets, because it is a complete segregation model is there. Macrofluid is not allowed to interact with the molecules of different age groups in the reactor. That's why the conversion is going to be different, and if the conversion is going to be different, then I should go for the mean conversion at the exit. If you want to find the average conversion, then obviously average is there, because conversion is different for each packets. Then how can I find the conversion at that average? The average conversion is found to be what? Summation of, means in time t and t plus dt, how much fraction of the tracer is coming, how much fraction of the molecules are coming, because when they are just about to come out throughout the inlet, they are not going to interact. Throughout the inlet to exit, they are not going to interact. But at the moment of exiting, the molecules of different age groups are going to mix. Try to understand here. Let's say they are the molecules of 2 seconds. Here all the molecules of 2 seconds. Here all the packets, it is a packets of 3 seconds. They are not going to interact throughout the reactor. But when they are about to come, when they are just about to come, what happens? They are going to mix to each other. And now if you know in time t and t plus dt how much fraction of the molecules are coming out, so let's say xt is the conversion, and if you are going to this multiply this xt with the fraction of the material which is coming out, it is called et into delta t. And if you are going to add for all time, you are getting the mean conversion. Is this clear, ma'am? Means they are not going to interact throughout the reactor, but when they are just about to exit, they are going to mix with each other of different age groups. And if you want to find the mean of that, we should sum up all. So how can make sum up? Because let's say at time t the conversion is xt, and in time t plus dt the fraction of the material which are coming out is et in dt. Ma'am, we should not go for expectancy. Forgot about expectancy, ma'am. Now it is clear, ma'am? Forgot about expectancy. Now similarly, if you have a continuous function is there, then what you should do, the mean conversion I can calculate by x of t into e of t into dt. Clear? 0 to infinity. For all time you can add, and then you can find the mean conversion, and that xt you can find the batch reactor formula, and this is the mean conversion. Now it is clear? And if you want to show the representation of the maximum Mason model is what? So complete segregation model is there. Input is there. You can see here T1, here T2, T3, T4, T5. All is going to match at the common point here at the output. What happened in this case? You can see here T1, T2, T1 is the residence time is T1, here for this T2, here T3, here T4, here T5. It means the residence time for each fluid elements are going to be different, but at the time of exit they are going to mix of all different age group here, but throughout inlet to exit they are not going to interact. This is the schematic representation. Representation of segregation model. Now I think you got here. Means this is the all the packets of the molecules which have residence time T1, here T2, here T3, here T4, here T5. They are not going to interact in any way from inlet to exit, but at the exit they are going to mix. And then if you want to find the conversion, then we should go for what? At molecules of different age groups are going to interact just about to exit, but throughout inlet to exit they are not going to interact. That is called as quality of macro fluid. This is model, and this is the model of micro mixing. The extent of the model of micro mixing, which assumes the fluid to be macro fluid, it is called as complete segregation model. Now it is clear, and in that we can find the conversion by this formula. This is the conversion by zero parameter model called as complete segregation. If the fluid assumes the complete segregation, then I can use this model. Okay, is this clear? So if it is given the fluid is macro fluid, then always you can find the conversion. This is 0 to infinity x of t into e of t into dt. Is this clear, guys? Or in terms of concentration, in term of concentration, This is macro fluid, and this is by the batch reactor. This you can find by, I told you already. In terms of concentration, how can I write? Since x bar, I can write 1 minus Ca bar upon Ca naught of macro fluid. Okay, and this Xa as a T, it is 1 minus Cat upon Ca naught from batch reactor formula. Then you can put here x bar as a replace 1 minus Ca bar upon Ca naught of macro fluid is equal to integration 0 to infinity one minus Cat upon Ca naught E of t into dt. Then please here if you multiply here 0 to infinity E of t dt minus 0 to infinity Ca of t upon Ca naught E of t into dt, and that is 1, you know very well, and 1 minus Ca bar upon Ca naught, 1 cancel. Then you can also write Ca bar upon Ca naught of macro fluid is equal to 0 to infinity Ca of t upon Ca naught E of t into dt. Is this clear, guys? Yes or no? This you can obtain from the batch reactor formula, Ca upon Ca naught. Here average concentration, here simple concentration of any packets by batch formula. This is conversion, this is the mean concentration. Means that is the, if we are going to assume which model, if the flow in the reactor follow which model, macro fluid or micro mixing model, micro mixing of which model, complete segregation, then I can use this formula. Okay, Anushka. The two formula, one is mean concentration conversion form and concentration form. You can use any of them. So this formula you can use to find out conversion in the real reactor which follow which model of micro mixing, complete segregation or maximum mixedness. Please tell me, Anushka. This formula you can find the conversion of any order, either first order or second order or any order. But the flow in that real vessel must follow the complete segregation model, and the complete segregation model is going to be shown by which types of fluid? Which types of fluid is going to show complete segregation of macro fluid? Any example of macro fluid, can you tell me? Yeah. Very good. Now the next is called as microfluid. The model of micromixing which assumes the fluid as a microfluid is called as maximum mixedness model. Then what is the quality of microfluid? Just opposite to the macro. In microfluid, in this fluid, the mixing of fluid element of different ages, mixing of fluid element of different ages is assumed to take place, is assumed to take place at the earliest possible time, at earliest possible time. And this model of micro mixing, this model of micro mixing is called as maximum mixedness model. Okay, and in this case, if you want to find the conversion, then you should go for dx upon, although it is not in our syllabus, only you should know here, dx upon d lambda. Dx is conversion, d lambda is life expectancy, is equal to minus Ra upon Ca naught plus E lambda upon 1 minus f of lambda into x. And that E lambda, f lambda, it is a value. By knowing the life expectancy, there is a data is there, there is table is there, you can put and find the value of E lambda, f lambda, and then you can find the conversion by this. Okay, although this is not in our syllabus, but what I am saying to you, try to understand. So in that microfluid, the two extent of micro mixing is there. One is called as complete segregation and maximum mixedness. In complete segregation, the fluid element of different ages are not allowed to mix, but here in the fluid element of different age groups are allowed to mix as early as possible. It means here the mixing is earliest, and in the microfluid the mixing is latest. Means microfluid has not tendency to mix, but the microfluid have tendency to mix. Okay, now here if you see the schematic representation here, oh, how many of you got this point? So this is called as maximum mixedness model. I've told you already, maximum mixedness model. In that case, because here the fluid elements of different age groups, different life expectancy are allowed to mix. That's why the conversion will depend upon, because here the fluid elements of different in the microfluid, the fluid elements of different age groups are not allowed to mix, but here the fluid elements of different age groups are allowed to mix. That's why it was some complex. What I'm saying to try to understand, the two extent of micro mixing is there, two extent of model is there, Sujata. So what I'm saying here, all the real reactor, so there are two extent, is there of micro mixing, two extent, one is this one, other is this one. So all real reactor or all the reactor have a conversion lies between these two extent, yes or no? Their extent, their limit, extent is minimum and maximum. The conversion in the reactor is lie between these two extent of the mixing. Whatever conversion you got from here and whatever conversion you got from here, it will lie always between these two, because here the mixing is latest and here mixing is earliest. बोलो क्लियर है, earliest possible. And the conversion in the reactor is lie between these two extent of the mixing. Okay guys, now listen carefully. One more thing I would like to clear here. One by one try to understand here. Please listen, Mehna. Now in this case, what happen if you are going to enter, what happen if you are allowed to enter a listen, if you are going to allow, you have a two reactor, let's say batch reactor, plug flow reactor, and you have a MFR, batch, PFR and MFR, am I right? Now they are ideal. Let's say if you are allowed to enter the macro fluid in a batch and PFR, what happen? If you are going to allow the macro fluid, means complete segregation, the fluid which follow the complete segregation model, if you are going to enter the macro fluid in a batch and PFR, what happen? Since it's common sense in the batch reactor, because as macro fluid is going to enter, and macro fluid are the fluid which have not tendency to mix to each other, means every microfluid, every packet will spend the same time in a batch, yes or no? Every fluid element will spend same time in a batch reactor, because batch reactor is going to be carried out for the common time, yes or no? They are not allowed to come unless the reaction is going to complete. Just use common sense, what I am saying to you. If you are allowed to enter the macro fluid in a batch reactor, you have a batch reactor is there, and here macro fluid is there, macro fluid. When you have batch reactor and you are going to allow the macro fluid, and since macro fluid has a, by definition, the macro fluid has not tendency to, by definition macro fluid have late mixing or early mixing, please tell me. By the definition, macro fluid have early mixing or late mixing? Yeah, same thing happen in the PFR also. If you are going to allow to enter the macro fluid in the PFR again, and PFR has obviously tendency to not to mix. By definition, the macro fluid have latest mixing. Yeah, latest mixing is there. So if you are going to enter in a batch reactor, they will spend the same time, yes or no? Yeah, it means CM mean equal to CA. Yeah, very good. CM mean is found to be C, excellent. And CM mean equal to CA, it means whatever formula we write, listen, whatever formula we derive so far, like in a CSTR and MFR, that is only for microfluid. Whatever formula I derive, let's say V upon F naught, whatever formula we derived previously, that is only for microfluid, means V upon F naught is equal to XA upon minus RA, or V upon F naught is equal to 0 to XA dXA upon minus RA. This is only for which fluid? Therefore microfluid, in it means I can use the PFR in a batch, sorry, not in CSTR, be careful, except for the CSTR, whatever formula we derived for the batch and for the PFR, I can use directly. Now what happen if you are going to enter the microfluid in the CSTR? What I'm saying, now I have two fluid, one is macrofluid, another is microfluid. If you are going to enter the microfluid in, let's say if you are going to enter microfluid in a CSTR, then what happen? Sorry, in a batch and PFR, when you are going to enter microfluid in the batch and PFR, and since in the microfluid they have tendency to mix, by definition microfluid are the earliest mixing, but again in the batch and PFR what happen? there is a latest mixing is there, yes or no? Either the fluid is, by definition microfluid is earliest mixing, but when they are going to enter in a PFR, when they are going to enter in the PFR, they are moving in form of flux, and the mixing is latest, yes or no? It means the mixing is early or late. It will also depend upon the types of reactor we are going to use. Yes or no? Please tell me. When you are going to enter the microfluid, when you are going to enter the microfluid in a batch, or let's say in a plug flow reactor, if you are going to enter the microfluid in a plug flow reactor, so although by definition microfluid have earliest mixing, but when the microfluid is going to enter in a plug flow reactor, it always have a latest mixing, yes or no? Because in the plug flow reactor, if it is ideal plug flow reactor, then mixing is not allowed. Means molecules of same age groups, here T1, here T2, here T3, like that, yes or no? Because they are plug flow reactor. Although the fluid have tendency to mix as early as possible, but when they are allowed, to mix, then only mix. Now in the PFR they are not allowed to mix, because it is plug flow reactor, you know very well. By definition, the microfluid is a fluid which have a tendency to mix when they are allowed to mix, when they are allowed to in the contact. But in the plug flow reactor, so in the plug flow reactor, either your microfluid or macrofluid, you can find the same formula as you derived. Now listen, I am talking about only micro, not macro. Listen, as far as microfluid is concerned, whatever equation you derived, it means performance equation, whatever performance equation you write here for V upon F naught equal to 0 to xa dxa upon minus RA, that is for the microfluid. Okay, same you can use here. Whatever formula we discussed so far, this is only for that we discussed in your BTA course or before this non-ideal, that is only for microfluid. Same in the case of batch reactor, same in the case of batch. And now what about in CSTR? When you have a CSTR is there, and when you are going to enter the microfluid, if you are going to allow to enter the microfluid in CSTR the fluids are different, are allowed to mix, because here mixing is there, huh? Then obviously here the mixing is earliest. So although the same microfluid have latest mixing in the PFR, and same microfluid have earliest mixing in the CSTR, yes or no? So here I can use simple V upon F naught, whatever performance equation I derive for 0 to xa, xa upon minus R at exit. This is for the earliest mixing in the CSTR. So for microfluid, whatever formula I have derived, that was only for which types of fluid? Microfluid. Means where we have assumed कि fluid have a tendency to allow to mix as early as possible if they are allowed. If they are allowed, अगर उनको allow किया जाता है तो. But if they don't allow, they will not mix. It's common sense. Just like in the PFR, in the although the fluid have tendency to mix when they are allowed, called microfluid. Yes or no? So for microfluid, whatever equation you have used, if the fluid is microfluid, then you should not worry for that. Either for any order reaction is there, either first order or second order, you can simply use the performance equation that you derived earlier. You can write that right. It is clear if the fluid is micro. But the problem is that only when the fluid is macro. So for microfluid, you should not worry. Whatever formula you have derived for the CSTR, PFR and batch, you can directly use. Is this clear? Yes or no? How many of you got this point? Mr. Shankar. For microfluid, although by definition the microfluid has earliest mixing, but when they are going to allowed in the PFR, they are not allowed to mix. That's why their latest mixing is there. mixing is latest for the microfluid, or now same come for macrofluid. When you have macrofluid, my dear student, and when the macrofluid is entering in the PFR, what happened? Again the latest mixing is there, yes or no? When the macrofluid is entering in a plug flow reactor, again the latest mixing is there. Again you can find the same performance equation as you found earlier. Yes or no? Same in a batch also. In the batch, although they have macrofluid is there, but the residence time is same for all. That's why conversion is same. We can find the same formula as we found for the batch reactor. But the problem is only in the mixed flow reactor. When the macrofluid is entering in the mixed flow reactor, what happened? Try to think yourself. When the macrofluid is entering in the MFR, what happened? When they are allowed to mix, they will not mix. I told you. Then you can't find the conversion. We can't find the same performance equation as we derived in the last for micro. Mr. Raz. When you are going to allow to enter the macrofluid in the CSTR, then you can't use the formula of performance equation as you did in the last, because in the macrofluid they have not tendency to mix when they allow to mix, and in the CSTR they allow to mix but they will not mix because they are macrofluid. Yeah, in that case I can found the conversion in the CSTR for the macrofluid as which formula? This formula as I describe here for macrofluid. Am I right? But if macrofluid is there, then you can find the same formula by using the performance equation as we did earlier. So all the formula I written before this non-ideal chapter is only for which fluid? Please tell me. Anushka, Sujata, whatever formula I had written for conversion calculation or performance equation, that is only for microfluid. मेहना क्लियर है या नहीं? The problem is with the macrofluid and only in the CSTR. Very good. The problem is with the macrofluid and when it is going to happen in CSTR. When the macrofluid is going to enter in the CSTR, when the macrofluid is entering in the PFR, then no problem. Again the mixing is latest. But when the macrofluid is entering in the CSTR, then they will not mix. But when the microfluid is entering in the CSTR, obviously they will mix because they have tendency to mix when they are allowed, and that is happening in the CSTR. But when the macrofluid entering CSTR, the tendency of reactor is to mix, but they are not allowed to mix because they have not tendency to mix when they are allowed. That's why in that case we can find the conversion by this formula. Yes or no? They will act as teeny batch reactor. Is this clear? And that's what I'm saying to you. The conversion in the reactor will lie between these two extent of the conversion, macro mixing and micro mixing. Clear? Sorry, for macrofluid and macrofluid. I'm sorry. So my dear student, this formula x bar of t is equal to 0 to infinity x of t into e of t into dt, that you can use for what? Macro fluid in CSTR, or for only macro fluid. And if you can check, please, what I'm saying to you, try to understand here. So try to understand, Mehna. Let's say x bar of t, this is 0 to infinity x of t into e of t into dt. Let's say you have a first order reaction, or let's say second order reaction is there. Second order reaction is there, having k is equal to, let's say, 1. So for second order reaction, minus Ra is equal to, let's say, k into Ca square. Is this clear? And you have to find out conversion in a PFR. Conversion in a PFR. Try to understand, sir. So I told you this xt you can find from the batch formula. So for second order reaction, what is the xt for the batch? Let's say I'm going to use the macro fluid entering in a PFR. Although I'm just assuming, try to understand here. I'm going to use this formula for finding out the conversion for the macro fluid in a PFR. You know, xt for the batch, this formula I can use for xt in a batch. And for the second order reaction, you know, ki minus dCA upon dt, or you can say general formula Ca ki power. Liquid phase reaction is there, then I can write Ca ki power 1 minus n minus Ca naught ki power 1 minus n equal to k into n minus 1 into t. This formula is there. Then for second order reaction, this is 1 upon Ca minus 1 upon Ca naught is equal to k into t. Then I can write here, I think this is 1 upon Ca naught 1 minus xa minus 1 upon Ca naught equal to kt. I think xa upon 1 minus xa is equal to kt. Then xa is equal to kt upon 1 k into Ca naught, sorry, k Ca naught into t upon 1 plus k Ca naught into t by the batch formula. If you put in this equation here, my dear student, then x bar of t is equal to 0 to infinity k Ca naught into t upon 1 plus k Ca naught into t into e of t for the batch is delta t minus tau. Am I right? Sorry, delta t. For the plug flow, what is ET curve? Delta t minus tau p. Yeah. Into dt. ET curve for this. Am I right? For the plug flow reactor. And I think, my dear student, by the property of Dirac delta function, you should know x bar t should be here, function of t is there, then replaced by the tau p, k Ca naught into tau p upon 1 plus k Ca naught into tau p. Is this clear? Yes or no? This is the mean conversion that you are getting here. Now please check if we are going to use the simple PFR equation that we derived earlier, just like V upon Fa naught is equal to 0 to xa dxa upon k into Ca naught square 1 minus xa ka whole square. So V upon Fa naught is Ca naught into V naught, and this is 0 to xa dxa upon k Ca naught square 1 minus xa ka whole square. This Ca naught cancel, then this is tau here, tau into k into Ca naught equal to 0 to xa dxa upon 1 minus xa ka whole square. If you solve this equation, what you are getting? Anyone? Please solve. So here I use the same performance equation as for the microfluid, or just I derived, and here I am going to use the complete segregation model for the microfluid. So for example, if you are going to enter the microfluid in the PFR, please tell me, if you solve this equation, what you are getting? Anyone? Yes, very good. Xa upon 1 minus xa. And if you solve for XA, are you getting the same formula, K C A naught in tau upon 1 plus K C A naught in tau? Are you getting the same formula, yes or no? Either for assuming this model or by assuming this model, you will get the same formula, yes or no? And why it is going to happen? Are you getting a point? Why either for the macro or for the microfluid? Because either is a macrofluid or microfluid, when they are going to enter in the plug flow reactor, the mixing is always latest. The mixing is always latest. Are you getting a point? Yes or no? Either it is microfluid or a microfluid. This is the for the microfluid, am I right? This is for microfluid formula. Anushka, just try to understand. Why you are getting same? Yeah, why it is same? Are you getting why it is same? It is same because either it is a macrofluid or a microfluid. But when they are entering in the plug flow reactor, always the mixing is latest. That's why. Are you getting a point? Yes or no? Bolo, clear? Yeah, very good, Pranjal. Same for batch also, yeah. Same thing is for the batch also. Now, but when you are going to enter in CSTR, one is macro, other micro, and second order reaction, again second order reaction is there. So in CSTR for microfluid, listen, for microfluid, you know, for second order reaction in CSTR, V upon Fa naught is equal to XA upon K into C naught square into 1 minus XA ka whole square. Then this is tau upon C naught is K is equal to XA upon 1 minus XA ka whole square, and this is C naught ka square. Then tau K into C naught is equal to XA upon 1 minus XA ka whole square. And if you solve, you will get the quadratic equation. If you assume the tau is equal to 1, K is equal to 1, CA not equal to 1, you can please solve for XA. If this is found to be 1, then please tell me what is the value of XA here. अभी जितना बता रहा हूँ तो सुनो. मैम बैच में क्या होगा कि if you are going to enter either macro or micro, every fluid have same resonance time ना. Either they are allowed to mix or not allowed to mix, but they will come from the reactor at the same time. Either they form the cluster of the different age groups, but they are all cluster have same age group, because every cluster will come out from the reactor at the same time. That's why either it is micro or macro, you will get the same conversion. मेहना मैम समझ में आया नहीं आया भाई? अगर आपको बैच में डाल दिया गया, इफ यू आर गोइंग टू अलाउ टू एंटर इन द बैच, either it is macro or micro, either it is complete segregation or maximum mixedness, but all the fluids elements of different age groups are allowed at the same time. So XA is found to be 0.382. very good if you cross verify. This is by assuming the microfluid. If the macrofluid is going to enter here, then I can use the formula for x of t is equal to 0 to infinity x of t into e of t into dt. Yes or no? Now x of t I can find the batch formula for second order reaction. For second order reaction from the batch, I told you already, this is found to be kt c naught upon 1 plus k c naught t. and KCA0 T is found to be 1. The XA from the batch is found to be K into CA0 into T upon 1 plus K into CA0 into T. Although KCA0 is 1 here, so T upon 1 plus T. Please, if you solve here 0 to infinity T upon 1 plus T into ET for the CSTR is what? 1 upon Tm tau m for CSTR e की power minus T upon tau m into dt. 1 upon tau m is outside, 1 upon tau m, 0 to infinity T upon 1 plus T into e की power minus T upon Tm into dt. Now if you solve, my dear student, you will find the different conversion here. Can you tell me? This is the exponential integral. It is special integral is there. You can't solve in this way. So this conversion is not found to be same for second order reaction. Are you getting why? Obviously it should be different. Why? Because when the microfluid is entering in the CSTR, the earliest mixing is there. But when the microfluid is entering in the CSTR, the latest mixing is there. And can you tell me, if the order is second order, n is more than 2, in which case it is first case, second case, in which case the conversion is found to be more? Can you tell me? In which case you will find this more conversion? Obviously this will be different. Just use your common sense and tell me, if n is more than 2, just revise the concept of CSTR and PFR in series, and one is PFR and CSTR in series, and then you can conclude here. When order is more than 1, which is favored? And that you can't find from here, my dear student. Obviously second order is there. My question is that, Sujata, in which reactor, first and second, in which case you will find the more conversion? Obviously in second case you will find the more conversion. Why? Because here the mixing is latest, and that is proved here. That is going to prove, if you solve this equation, you will find the conversion is more than 0.38. The reason is that because, and that is going to prove कि always the higher order favors the latest mixing. Late mixing is favored. When the order is more than 1, always the favored by late mixing, and late mixing in the second case. Is this clear? And that's what I want to say. And that was the reason why you got the different conversion for the order more than 1 and less than 1. And the same thing, if you check for the half order reaction, my dear student, if you check for the half order reaction, in these two cases, please tell me in which case you will get the more conversion. Then you will find, my dear student, in this case where the mixing is latest, you will find the lower conversion as compared to here, because here in this case the mixing is earliest. That's proof कि मैम आप समझने की कोशिश ही नहीं कर रही हैं, प्रॉब्लम ये है. Yeah, very good. Ma'am, here it is a macro. I've told you it is a micro and macro. I have compared with the both two here, because I told you when you are going to enter the microfluid either in CSTR or in PFR or any reactor, you will find the same conversion as we derived and before the class, before the non-ideal chapter. But when the macro fluid is, I'm talking about, again the macro fluid in the in the PFR, in the batch, you will find the same. But when the macro fluid is entering in the CSTR, then the conversion is going to be different than the micro fluid. Yeah, very good. And that's what the result is. Mr. Raj, is this clear? Reason clear है? Because for order less than 1, the mixing is earliest mixing is favored. When the order is less than 1, I've told you already, the early mixing is favored. And early mixing is what? In which? When the fluid is microfluid. Am I right? While in this case, when you are going to enter in the plug flow reactor, either the fluid is micro or macro, always in both cases. What I'm saying to you, either macro or micro. In both cases, the mixing is latest. But when you are going to enter in a CSTR, for micro, earliest mixing is there. And for macro, in the CSTR, latest mixing is there. Is this clear? Mr. Raj, the thing is very clear. When we are going to enter the macro or micro fluid, always the mixing is latest. Always mixing is latest. It means whatever formula we derived earlier before this non-ideal, you can use directly the same for any order of reaction. But the fluid must be either macro or micro. But when the same in the batch, if it is batch and PFR, it is found to be same. But if I'm talking about CSTR, when I'm talking, it is a batch here, no input, no output, but I'm talking about the CSTR, then depending upon the fluid is macro or micro. If the fluid is macro, for macro fluid, what happened? For macro fluid, latest mixing is there. And here for micro fluid, in this case, earliest mixing is there. Here mixing are latest, and that is the nature of the PFR. Here the mixing micro and macro mixing is latest and earliest here, and that's why you got different conversion in that case. So what is saying here, XA for macro fluid for n more than 1, XA for macro fluid, macro not micro. For micro, no change, we are same. XA macro is more than XA micro. Yes or no? For n less than 1, XA micro and for n equal to 1, all are same. And that is in the CSTR only. Okay. Now, how many of you got this point? So whenever a macro fluid or a micro fluid is entering in this PFR, you can use that formula as you derived before this chapter. But when the microfluid is entering in a CSTR, then you should be take care for that. In that case, you should always, for the microfluid in the CSTR, I should go for, because in this case the mixing is latest. Microfluid has a nature to not allow to mix, and here CSTR is allowed to mix here. That's why the conversion is different here, and we should go for this formula. XA bar is equal to integration 0 to infinity x of t e of t dt. And that's why here I told you now, in this CSTR case you got a different NIVA, but in the PFR you got the same formula. You can check for the half order as well. You can also check for the half order in the PFR, either macro or micro. You will get the same formula as you derived. For example, let us see here. If I am going to do this half order reaction for the PFR, the last here, if we are going to use, let's say the PFR is there, and I am going to use the microfluid, and I told you for microfluid I can directly use the formula for PFR is V upon Fa naught is equal to 0 to XA dXA upon K into Ca naught k power half 1 minus Xa k power half. So this is tau K into Ca naught is equal to 0 to Xa into dXA upon 1 minus Xa k power half. Please, anyone can solve this? And if you are using the microfluid in the PFR, and if I am going to use this formula, x bar of t is equal to 0 to infinity x of t into e of t into dt, then x of t for the half order reaction is what? You know, for half order reaction for the batch formula, this is always, we should go for the batch formula. This is 1 upon Ca naught k power 1 minus half minus Ca k power 1 minus half is equal to k into t. What formula I written here? K n minus 1 t. K n minus 1, n is half, it means minus half into t. Then Ca naught k power half minus Ca naught k power half into 1 minus Xa k power half is equal to k into minus half into t. From this equation, please, Ca naught k power half 1 minus Xa k power half is equal to minus k by 2 into t. Please solve for Xa. Then 1 minus Xa k power half is equal to minus k by 2 into t into Ca naught k power minus half. Then 1 minus Xa k power half is equal to 1 plus k by 2 into t into Ca naught k power minus half. And let's say k is 1 and Ca naught is 1. To simplify, then 1 minus Xa k power half is equal to 1 plus t by 2. Am I right? Then here it will be square. 1 minus Xa is equal to 1 plus t by 2 ka whole square. Then Xa is equal to 1 minus 1 plus t by 2 ka whole square. This is Xa. If you solve for if k and Ca naught equal to 1, and put in this formula, Mehna 0 to infinity, here 1 minus 1 minus t by 2 का whole square into e of delta t minus tau p into dt. And if you solve this with t will be tau p, then answer is 1 minus tau p by 2 का whole square. This is the formula for xt. So from here we found this formula for xt, and please solve from this. क्या पॉजिटिव आएगा? हाँ सुजाता, प्लीज सॉल्व फ्रॉम एक्स से हेयर ना, के सी नॉट को 1 कर लो, और जो भी यहाँ से आंसर आया है, जो वट एवर यू गॉट हेयर, सॉल्व दिस एंड सॉल्व फॉर एक्स से, एंड प्लीज चेक, अदरवाइज यू कैन पुट द वैल्यू एंड यू कैन चेक. एनीवन कैन क्रॉस वेरीफाई? सुजाता, you are very good in integration, and that's very best part for you. I see many times ki you always did the integration very fast, and that's the very best part for you. No, it's minus n minus 1 in t is there. Please, anyone? Anushka? Please cross verify. What XA expression we are getting, Mehna? What XA expression we are getting? Because I should not do this. This you can do yourself. Please, Shankar, check for half order reaction by for the macro and for the micro. ले आओ तो. हाँ तो ले आओ आज. Please put the k equal to 1 and c naught equal to 1. Anyone can cross verify, yes or no? हाँ but अनुष्का चेक कर रहे हो? मेहना बोलो भाई, चेक कर रहे हो या नहीं? Okay, great. हाँ, same thing I written now, Mr. Raj, because k c naught is 1, same thing I written here. And please solve for this equation. Please solve this integration and solve for the xa. K c naught equal to 1. Tau is equal to, it is tau p here. Zero to xa dxa upon 1 minus xa की power half. Solve for this integration and solve for xa. What value you are getting, Mr. Raj? Yeah, you did correctly, but please do this for. सही है? हाँ तो x से निकालो ना मिस्टर राज, प्लीज सॉल्व फॉर x as you got here. तो this will be 1 minus x के power half is equal to 1 minus tau k by 2 into c naught के power half. Okay, then 1 minus x is equal to 1 minus tau k upon 2 into c naught के power half का whole square. Then x is equal to 1 minus tau k upon 2 into c naught के power half. That's what का whole square. Is this clear, Mr. Raz? Yes or no? So what I'm saying, and it should be, because I told you कि when you are entering in the PFR for any order of reaction, either micro or macro, you should be relaxed, and the same in the batch, you will always find the same conversion. Yes or no? But you will get the different answer in the case of batch, in the case of CSTR. Reason is clear? Reason is clear, yes or no? समझ गया? Now it is clear, relax. So result is, you can please, it's my humble request, you should please revise the notes and try to write immediately in your own languages in your notes, Mr. Raj. This is all about your zero parameter model. So when you have a PFR and it is talking about micro or microfluid, you should close your eyes and solve the same equation as you write for the plug flow reactor derived. But when it is talking about the CSTR, then you should be take care for that. Okay, and reason is very clear, because either microfluid or macrofluid, always the mixing is latest in the PFR. But when the microfluid is entering in CSTR, the mixing is earliest. When the macrofluid is entering in the CSTR, mixing is latest. That's why the conversion is different. Okay, clear? So along with the types of fluid, it also depends upon the types of reactor. It means types of RTD, you can say. Okay, so Mr. Raj, Mr. Nebha, everything is clear. Anushka, Sujata, clear? So thank you so much for this. And the only topic that is left is axial displacement model. I will take the in next 1 hour. I will complete the in the next class. In the first 1 hour, I will complete this topic, and we'll solve the numerical problem based on that also. Okay. Now, please, people, you peoples are now. Please give me feedback, because I tried my best to clear the topic of non-ideal, zero parameter model, first parameter model, and multi-parameter model, and try to link and try to connect and try to revise. If you will not revise, everything will get forget. That's why it's my humble request, try to revise this by tomorrow. Okay, and try to write all the points in your own languages. Thank you so much. Have a nice day.